Okay, so today's plan, pretty simple, just continue on with Bayes' theorem. We might wrap it up today. We might go over a little bit into Wednesday's class with Bayes' theorem. And the quote of the day today from Marcus Aurelius, the Roman philosopher. Uh, he was one of the Stoic philosophers, and Stoicism has become it's kind of all the rage these days, I suppose. The quote is often uh, just phrased as be one. But that's really taken from this line, start arguing about, not start, stop arguing about what it means to be a good man, be one. So in other words, oftentimes it feels more comfortable to kind of sit around and debate what the right thing to do is instead of actually just getting out there and taking a step forward, right? We can sit here and, uh, kind of talk about something forever and ad nauseum and never actually make any progress. But at some point, you kind of know what you got to do. You just got to go out and do it. I think that's what it's getting at. Okay, so really quick, let's recall how Bayes' theorem works. Bayes' theorem looks like this. Probability of A given B equals probability of B given A times probability of A over probability of B. Or if we have, say, probability of B split into multiple kind of like sub-events, then we could break that denominator into something like this, where really we're looking at the proportion of the denominator that the numerator makes up. And we saw an example of this last time. We'll see a couple more examples today. And we briefly talked about the kind of two ways to interpret this. These two interpretations don't say something different about the mathematics itself. Both interpretations, both of the two paradigms agree on this theorem. Both kind of the frequentist approach and the Bayesian approach agree that this mathematical rule is true. But it's a question of whenever you overlay this idea of probability onto something in the real world, what does it kind of, in a sense, mean? One interpretation is just that, well, I want to find probability of A given B, but maybe I'm given information. Maybe it's more natural for me to find information of the form probability of B given A. My condition uh, of the information that I can easily find is the opposite of the condition that I want. So I can just flip the condition to get the different conditional probability, and I can find probability of B given A and use that to help me answer probability of A given B, provided that I multiply by this ratio, probability of A over probability of B. So it's a nice little trick to allow us to flip the condition, which event we're conditioning on, which event is before versus after the given sign. But I think there's a deeper meaning to it that really forms kind of the foundation of what we would call Bayesian statistics, a different way of looking at how statistics is applied to the real world and what it, in some sense, means to apply this structure of probability, this mathematical structure that, again, both sides agree on, the mathematics. But what does it mean when it applies to the real world? When I look out the window and say, I think there's a 40% chance it's going to rain today, what do I mean by that? So another way to look at it is, again, same mathematics. It's just which of these factors we pop off the numerator. I can look at probability of A, and I can look at that turning into probability of A given B. In other words, I have some event A that's like my current worldview, my probability of event A happening, maybe the probability that it snows outside or something like that. And then I learn a new piece of information. I walk outside today and I realize, oh, wait, it's actually pretty cold outside. Given the knowledge that it's pretty cold outside and it's not like 70 degrees like it was late last week, I say, okay, well, maybe now that I have a new piece of information, I now know that it's pretty cold outside. Maybe that updates my probability, my estimate of the likelihood that it snows today. Right. So I have a certain worldview based on a certain amount of information, a certain experience. I say the probability it snows today, I think, is 10%. Maybe that's what the probability has historically been on St. Patty's Day or something. I walk outside and I realize it's pretty cold. And I might say, okay, I think now, in light of this new piece of information, the probability it's going to snow has gone up. Or if I walked outside and it was warm, I would think the probability of it snowing has gone down. So as new information comes in, I don't want to just ignore the information and dig in my heels and say, oh, well, even though I walk outside and maybe in a different year it happened to be 70 degrees today, well, I think it's still going to just be as likely to snow as I thought it was before that piece of information. That doesn't make a lot of sense, but I also don't want to completely jump ship and ignore all of my previous knowledge and just say, oh, it's cold outside today. It tends to snow when it's cold, so I think it's likely it's going to snow today. Maybe it doesn't typically snow in March. So, right, I want to incorporate the new information with the existing worldview in kind of a reasonable and systematic way. And Bayes' theorem says if I have a worldview, let's call it probability of A, I have a new piece of information that comes about, namely that event B has occurred. Then I multiply probability of A by this ratio, probability of B given A over probability of B. And that's the systematic way to incorporate that new piece of information in with our existing worldview. Okay, so let's take a look at an example. I'm actually gonna go to just one note for my share for this so that it's a little bigger on your screen. We won't be using the calculator or the Excel file for a little while. So this way it'll be a little easier for you to read all of this. So let's look at an example. And I know we have quite a few medical folks in here, so I want to do a couple examples related to medicine. I think this is where this Bayesian idea can really shine. Is, we have a patient come in with a set of symptoms. We have a differential diagnosis. We have a set of diseases that are associated with those symptoms. And then maybe we do a test or we investigate a little further, something like that. We do a physical exam, whatever it may be. And then that moves some of those diseases a little bit higher, some of them a little bit lower on our differential, right? Some of them, our index of suspicion gets higher or lower based on new information that comes in. We don't take a piece of new information and, only look at that piece of information and forget about everything else that we had found out so far. But we also don't take a new piece of information and just ignore it. We want to combine those two together. So here we're looking at testing for cystic fibrosis carrier status. We're going to assume that cystic fibrosis is an autosomal recessive disease. So we need to talk a little bit about the medicine and so on as kind of an aside. This won't be part of, if you had a exam question or something like that, you wouldn't need to know all of this, but just trying to flesh it out a little bit so you see where these numbers come from and maybe understand the context a little bit better. So what is an autosomal recessive disease? Let's bump off to the side here. And I think most of us have in high school kind of seen some of these Punnett squares and Mendelian genetics and Mendelian inheritance and so on. But let's suppose that we have a trait that could either be like capital A or small a. So here capital A is dominant, small a is recessive. And I could have, let's say that mom has one version of one gene that's capital A, one that's small a. And let's say that dad also has one capital A and one small a. Now, what do we mean when we say that a gene is dominant or recessive, or that a trait is dominant or recessive? I'm not being super careful with my language here. So if there are folks who really know genetics, I'm using some of this language pretty flippantly here. So, I suppose traits are dominant versus recessive, not necessarily genes, but trying not to get too bogged down in the semantics. But sorry if it's irking some of you that know a little bit more about genetics. But what does this mean? Well, two things to keep in mind here. One is that each one of us, in essentially all of our cells, all of our somatic cells, for the most part. We have a cell, and in the nucleus, this is the nucleus, we have our genetic material, and we have like two copies of chromosome 1 and two copies of chromosome 2, and so on. We have two copies of each chromosome, except perhaps the sex chromosomes. So let's say that this trait is on chromosome 1. You got one copy of chromosome 1 from your dad and one copy from your mom. So when I'm saying that like dad or mom have like one capital A and one small a, that means both of them, like dad got a capital A given to him from his dad and say a small a from his mom, or vice versa. And then similarly with mom. Now, when they choose which one to pass along to their progeny, it's essentially chosen at random. So their kid could be capital A, capital A, capital A, small a, small a, capital A, or small a, small a. The second thing we need to realize is, what does it mean for a trait to be dominant or for an allele to be expressed in a dominant fashion? It means if there is, so maybe like trait capital A is like blue eyes or something. I think eyes might be multifactorial and probably not blue, but let's just pretend because that's the color that I have up next. So capital A is like blue something, blue hair. I don't know. We can make it silly. And small a, let's say, is green hair. Now, what it means for something to be dominant is that if there is any capital A at all, then the capital A wins out. So capital A, that person's going to have blue hair, blue eyes, whatever you want to pretend it is. But also in the capital A, small a's, the capital A kind of masks the small a. It doesn't appear as though the small a is there at all. It just, the person will have blue hair or whatever. But only if you have two small a's, then the person looks like a small a trait. So that's what it means to be recessive, is if small a is recessive if the only way that trait is expressed is if the person has two copies of small a and no copies of big A, no copies of the dominant trait that would mask it. Oh, okay. So we're assuming that CF, cystic fibrosis, is an autosomal recessive disease. Autosomal meaning that it's not one of the sex chromosomes like on X or Y, which can make things a little more complicated. So you need to inherit two mutant copies or two bad copies of the CFTR gene in order to have the disease. So like if just mom passes you a bad CFTR gene, but dad passes you a normal, you don't have the disease. And same thing if mom passes you a normal and dad passes you a bad one. But if both of them passed you a bad copy, then you would have the disease. Okay. Now, there are people, like say mom and dad here, that maybe have one dominant copy and one recessive copy. So if I look at mom's going to look blue, and dad is going to look blue because each of them have one copy of capital A. But notice that kind of like two blue people can actually have a green kid. What we call those people is these types of blue people, we call them carriers. Because two blue people can have a green kid because they're each carrying this this recessive copy. Now, if like dad was capital A, or if mom was capital A, then every one of their kids, at least in theory, would have a capital A, and then two blues like that are not carriers can only have blue kids. Again, roughly speaking, not presuming no spontaneous mutations, things like that. But the thing is that if you just look at a person and see that they're a blue hair person, whatever it may be, you can't really tell whether they have like two capital A's or one capital A and one small a. Right. So it is possible for two people who like look like they have blue hair to have a kid who has green hair. Or it's of course possible for two people that look like they have blue hair to have a kid that has blue hair. So we might be interested in knowing whether these folks who look blue, who look like capital A, actually have a small a hiding in the background or not. And we can do that by running a genetic test. Okay. So again, we call people carriers if they have kind of one dominant and one recessive copy. They're affected if they have two recessives. That's the green person down here is affected. And they would be not carriers if they have like two capital A's. They have two dominant copies. So let's suppose that the patient that we're looking at does not show signs of cystic fibrosis. They don't show signs of having the disease. So the person we're looking at, we're presuming, is not in this case, where they would have kind of two bad copies and therefore show symptoms of the disease. But let's suppose that this person's brother does have the disease, does have cystic fibrosis, so they have two bad copies of the disease. Or sorry, two disease copies of the two mutant copies of the gene. They have the disease, they have two bad copies of the gene. So essentially what we can presume then is that both of their parents are carriers. Now we can consider the person that we're interested in who doesn't look like they have CF. It doesn't look that they don't appear to have the disease. So we know they're not in this one square, but they could be in any of these three squares. Again, we're presuming that their parents are both carriers because their brother has the disease and they don't, and presumably their parents are unaffected as well. So there's a 1 in 3 chance of being in each of these three squares here, this one, or this one. And we notice that in two of them, the person's a carrier. They have one of the capital A's and one of the small a's. And in one of them, they're not a carrier. They have two capital A's. Okay, so after all of that was basically to say that for a person who has parents who are unaffected by the disease, but who has a sibling, a brother or a sister who is affected by the disease, and that person is not affected by the disease. So the person, their parents, not affected, but the sibling is, their probability of being a carrier is 2/3. Again, that's these two blocks out of the three blocks where they're not affected by the disease. And their probability of being a non-carrier is 1/3. So this is what we're taking to be our prior probability distribution. If I knew nothing else other than the family history, then I would estimate that this patient's probability of being a carrier for cystic fibrosis is 2/3, and their probability of being a non-carrier is 1/3. And we're assuming that their probability of having the disease being down here is 0. This is a severe enough disease that they would show signs and symptoms if they had it. Now, our patient might be interested in having kids, so they find a spouse. They want to start looking at having kids, but they realize that this isn't a super uncommon disease for people to be, or mutation for people to be carrying. They're concerned about the potential that their kid might have the disease. So they would like to undergo a test for carrier status. So the way that these tests work, and again, we're kind of oversimplifying things a bit here, but this is a genetic test. You take a blood draw, you send it in. They look for certain genetic variants that are known to cause cystic fibrosis. Now, there are a whole lot of variants that are known to cause cystic fibrosis. There are even more variants that might cause it in some situations and maybe not in others, and it's kind of complicated. So a lot of these tests, the tests are run differently in different labs, but a lot of these tests might look for, say, the 20 or 25 most common and most certain disease-causing mutations. So if you have one of these disease-causing mutations, it's almost certain to show up on a genetic test. But you could have one of the other disease-causing mutations that you're carrying around, and that might not show up on the genetic test. It might be a false negative. So this test is reported to be 90% sensitive and 100% specific. So let's take a little digression and talk about what do we mean when we say a true negative or a false negative, or a true positive or false positive? What do we mean by sensitivity and specificity? Okay, so if I'm looking at a patient and I'm considering whether I think they have the disease, there's an actual status. The actual status is they could have the disease. In other words, they could be positive. Let me actually write that out, positive. Or they could not have the disease, no disease, that they're negative. So if you're being investigated for whether you have a disease, you kind of want the answer to be negative. There's, if you've ever seen The Office with Michael Scott, where Kevin gets a test result for, I think it was like skin cancer or something, and turned out negative, and Michael interpreted it the wrong way and thought it meant he had skin cancer and was all like feeling bad for him. And kind of the opposite of that. And then our test could indicate disease. It could indicate positive, indicating disease, or our test could come back negative, indicating no disease. And the important thing is that our tests aren't 100% accurate all the time, right? If the person has the disease, if they are positive and the test indicates positive, that's good. Let me write that check a little smaller so I can fit a little more in there. If the test comes back negative, indicating they have no disease and they actually don't have the disease, that's also good. But unfortunately, sometimes the test could come back positive, even for a patient that does not have the disease. That is an error. Or the test could come back negative, indicating no disease, for a patient who's actually positive, who actually has the disease. That is also an error. So this top left quadrant, this is where the test is positive and the patient is positive. So that's a true result. It's correct. And the result that was indicated was positive. This is our true positive rate. So a true positive is when the test indicates positive and the patient actually is positive, actually does have the disease. On the bottom right, the other kind of a good case, I mean, not good in the sense of having the disease, but good in the sense of performance of the test, is when the patient does not have the disease and the test indicates they do not have the disease. So that's a true result. It's correct. And what was indicated by the test was a negative. So that's a true negative down there on the bottom right. Now our two errors, we refer to these as false something because the test is giving a false impression of reality. The test is incorrect. The test result is discordant with the true status of the patient. If the test is positive, but the patient is negative, if the test indicates they have the disease, but the patient doesn't actually have the disease, then that's a false. And what is it, a false positive or negative? The only thing that we see is the test result, right? So we always base our statements off of the test result. We are not omniscient. We can't just tell whether the patient has a disease or not. If we could, we wouldn't be running the test. So this is a false positive. The test indicated positive, but it's incorrect. The patient actually is negative. And similarly down here on the bottom left, this is a false negative. The test indicated negative, but the patient's actually positive. So my test result is discordant with reality, it's false, and the test result was negative. And it also will help us to understand what this sensitivity and specificity and all this stuff is. It'll help us to think about how we might try to figure out what these numbers are for a given test. So if I have a given test, if I try to bring a test online, maybe testing for CF carrier status, what I would want to do is I would want to have a bunch of samples that were tested according to some gold standard that are maybe known positives, and a bunch of other samples that are known negatives. So I maybe take 100 samples that are known positives that I know for sure, the blood in these vials is from somebody who has the disease. So I have a group of folks, well, not of folks, of samples that I'm using to test my test over here that are, say, known positives that have known actual status being positive. And then I evaluate which ones of those come back positive versus negative. Probably if I run 100 of these, probably a couple of them are going to come back negative just by chance. My test cannot be perfect. So I'm probably going to get a couple of false negatives and hopefully a lot of true positives. So given that given that the actual status is disease, the actual status is positive, what's the probability the test is positive versus negative? That's something that I can get out of the process where I validate my test. And I could do something similar on the negative side. I could have a bunch of negative controls. I could have a bunch of samples that were tested in another lab or that were tested according to some gold standard and that are known to be negative. Of these known actual status negative samples, what proportion test negative versus positive? I hope that most of them test negative, but there's probably going to be some that result in a false positive. My test, again, I don't expect to be perfect. I just expect it to be good enough. And again, I can put these, say 100 known negative samples through my process, see what proportion come up negative versus positive, and I can find these two numbers that way. I would really like the blue boxes, the check mark boxes, to be large numbers and the red X boxes to be small numbers, so that my test, is kind of accurate most of the time, but makes a mistake every once in a while. So when we look at the sensitivity and specificity for a test, really what we're talking about is these blue boxes. So what's the probability of the disease or that a test is positive given the patient has the disease, given the patient is positive? That's our true positive rate, or that's our sensitivity. In other words, given that there's something there to be detected, what's the chance we detect it? If we have a very sensitive test, we detect most things that are actually there, right? You think of, for instance, like your fingertip is just a physically sensitive part of your body. If there's a little grain of sand or something on your desk and you run your fingertip across it, you're probably going to feel that grain of sand if it's there. If you run like your foot across it or something, your foot's much less sensitive, you might not feel it. So that's the probability of a positive test result, given that the patient is positive, given the patient has the disease or the thing that we're looking for. Right? This is run out of room in here, but this is probability. The test is positive, given the patient has the disease. Let's see, D, not a P. Similarly, my true negative box down here, this is the probability the test is negative, given the patient does not have the disease in reality. We would also kind of want that number to be high, the true negative rate. We want the true rates to be high. And we see that's what we call the specificity. In other words, my test is pretty specific. It's not just going to go around saying that there's a grain of rice everywhere. It's only going to say that there's a grain of rice if there actually is a grain of rice. So this is the specificity. So having a high specificity means the false positive rate, the claim by the test that the patient's positive when they're actually negative, that should be low. Or, if I run my finger across a desk with no grain of sand on it, I shouldn't very often imagine a grain of sand and say that there's one there when there actually isn't. Okay, so we're told for this test that the specificity is 100%. We probably would never want to really say 100% chance of something, but we're going to put it in here basically because it makes the arithmetic a lot easier to do. So the specificity is 100%. In other words, if the test calls positive, what's the chance that it's a false positive? If this is 100%, then this box up here is 0%. It never makes a false positive. If the test actually does find a match to one of the 20 or 25 genetic sequences it's looking for, then that match is actually there. It's not going to like imagine a match somehow. Now, again, we might take umbrage with putting an actual 100% here. We might say maybe 99.5% would be better, but we're not going to quibble over that detail here. That's not the goal of this example. The sensitivity, however, right, if the grain of rice is there, will I feel it with my finger? Or if there's a disease-causing mutation that this person's carrying, will my test identify it? That's actually not 100%, because remember I said there's a whole bunch of disease-causing mutations, and we can, number one, it's really hard to test for all of them, and number two, for some of them, we're not even really 100% sure if this specific mutation does cause the disease or not. So the person could have a disease-causing mutation, and we miss it because it's not one of the 20 or 25 that we're looking for that are the most common ones and the most well-established ones. So the sensitivity for this test is 90%. So this is 90%. In other words, we make a mistake and generate a false negative, say 10% of the times that the patient is actually a carrier. Right, 10% of the time we say, nope, we didn't find anything, but they actually have a mutation and maybe it's just not one of the ones that we looked for. Now, to be clear, like the results of these labs don't just say, no, we didn't find anything. They say, this is how this is how our assay works. Like we look for these 20 or these 25. We know that there are limitations to it and that's not perfect and all of that. So there's a lot more to it than just this. So what we're interested in is, suppose that, did I say that here? Here. Suppose that our patient tests negative. What's my updated probability he's a carrier? So before the patient went for this genetic test, just based on their family history, the signs and symptoms exhibited by their brother and the lack thereof exhibited by them and their parents, we said the probability of being a carrier is 2/3, probability of not being a carrier is 1/3. They go and have some blood drawn, have it sent away for this test. The test comes back and says your test result was negative. The test is indicating you're not a carrier. Well, again, our test isn't perfect. We don't just want to jump ship on any of our family history and say, okay, I'm absolutely certainly not a carrier now and move forward. We could be a carrier with one of the genetic mutations that the test just doesn't cover. We don't want to throw out the previous information, our prior distribution, but we also don't want to dig our heels in and say 2/3, 1/3 forever. I don't care about the test result. We don't want to do that either. We want to combine the kind of family history information that's embedded in this 2/3, 1/3 with the new information that our test result was negative for a test with this sensitivity and specificity. It seems like a really complicated thing to do, but it's really just an application of Bayes' theorem here. So really what I want to know is what is the updated probability our patient's a carrier given they test negative. We have the prior probability they were a carrier before the test information was back. Now that the test information is back and the test indicated negative, the test indicated they're not a carrier, what's the updated conditional probability of them being a carrier given the test result was negative? Well, what we have information about is probability of test result given actual status. What we want to know something about is probability of actual status given test result. My conditions are flipped. I want to be really careful and not just grab this number, probability of negative given carrier, 10%, and plop that here and be done with it. That's the opposite condition of this one. Those are not the same thing. But we can rephrase this question in terms of this information, again, by using Bayes' theorem. So this is probability of negative given carrier times probability of carrier over probability of negative. So the probability the person is a carrier given they test negative after incorporating this new information from the test, we use Bayes to flip that condition around, probability that they are, let me redo that negative sign there. I want to make it a little cleaner. There we go. What's the probability that their test result came back negative given they're a carrier times the prior probability from up here that they're a carrier divided by the total probability of this person getting a negative test. Well, we note that there are two ways from they get a negative test. They could get I've run out of colors. Maybe I can highlight. Two ways to get a negative test. They could get a false negative. They could have a negative test when they're actually a carrier, or they could get a true negative. They could have a negative test when they are actually not a carrier. So let me come off to the side here and say that, negative test is negative and carrier, or negative and not a carrier. This should start looking like the car example we did last time, right? The type, whatever, type 1 or whatever, type 2 car could come from plant 1 or plant 2. So we could have type 1 breaking down into type 1 and plant 1, or type 2 and type 1 and plant 2. I think that was how we said it last time. But I could break this denominator into probability of negative given carrier times probability of carrier. This is probability of testing negative and being a carrier. That's this event. I chose to break it up this way because that's the whole reason I'm doing this. I wouldn't want to break it up as probability of carrier given negative times probability of negative, because I'm looking for probability of carrier given negative. I don't know that. I want to break it up so it looks like the numerator. Plus, because this is an or, and these are mutually exclusive, I can't simultaneously be a carrier and a non-carrier. What's the probability of negative and not a carrier? That's probability of negative given non-carrier times probability of being a non-carrier. Okay, now where do all these pieces come from? In my numerator and denominator, I see some probabilities that are not conditional. These are my priors. These are the probabilities that I started with before the new piece of information came in. That's these ones up here. So probability of carrier, 2/3. And probability of non-carrier, 1/3. I have some conditionals as well. Well, let's start actually with this one down here. Probability of negative given non-carrier. So the test was negative. The test indicated the person is not a carrier, and they're actually not a carrier. That's simply the specificity, or that's just 100%. And I guess I'll use red for this one. Probability of negative given carrier. The test resulted in negative, but the patient actually has the disease. They actually are a carrier. That's a false negative. Remember, my false negative rate down here on the bottom left is 1 minus the true positive rate. That does seem a little bit strange. It seems like I did a double negative and this should be like the same idea, false negative versus true positive. But remember, the actual stays the same. So switching the test result from negative to positive is what switches the false to the true. So it's not actually a double negative, it's that the true versus false is reflecting the change from positive to negative. But we see that our false negative rate is 1 minus the true positive rate. It's 1 minus the sensitivity. My sensitivity was 90%. My false negative rate then is 10%. And what color did I make that red? Okay, so I'll make this 10%, or let's say 1/10. Now what can I do? I can multiply top and bottom by 30. So that gives me 2 over 2 plus 10. 2 over 12, or 1/6. So given the test result comes back negative, my updated probability of the person being a carrier is 1/6, or about, say, 17%. And now, of course, the probability they are not a carrier given the test result is negative, well, that's 1 minus 1/6. That's just the complementary event. Given the test result is negative, they must either be a carrier or a non-carrier, mutually exclusive, right? These are complementary events. 1 minus 1/6 is 5/6. Probability of non-carrier given negative test, or about 83%. And remember that our priors probability of being a carrier was 2/3, or 4/6, or about 67%. And their prior probability of being a non-carrier was 1/3, or 2/6, or about 33%. Our test result coming back negative, indicating no disease, it did not make the probability of being a non-carrier 100%. We didn't just jump ship on all of our previous knowledge and just say, just go with the test result, because the test isn't perfect. We meshed together the prior information that we had about things like family history and symptoms and so on. With the test result, we put those two pieces of information together systematically. And we see that the chance of not being a carrier went from 33% to 83%, or from 2/6 to 5/6, went up by a factor of 2.5. The chance of the risk of being a carrier went from 4/6 to 1/6, from about 70% to below 20%. It was cut by a factor of 4, but still not 0, right? The person could have got this negative test result and they could still be a carrier. And they would have to decide what to do with this. Do they want to look at other options? Do they want to still try to get pregnant? Do they want to, do more follow-up testing to try to, is there something else that they could do to, go to a bigger lab that tests more things that tests more parts of the gene that maybe has a higher sensitivity and kind of redo this? They would have to decide what to do now. Uh, we don't, again, keep in mind what we can answer with things like math and stats and what we can't answer. What should they do now? What decision should they make? That's not a question we can answer. But we can tell them that, okay, on the basis of your family history and this genetic test result, your risk of being a carrier is 17%. Maybe we also look at their spouse's risk of being a carrier. We look at if they were both carriers, then what's the probability that the kid would be affected? And maybe we boil all of that down into essentially, if the two of you have a kid, what's the chance that your kid has CF? How bad is CF if they get it? What are the other options? And then make a decision from there. So that's a wisdom type decision, not a math type decision. But we can use the math to give some data that might help inform that wisdom type decision. Now, here's an interesting question. This is an exercise, so you can follow through with very similar calculations to up here and use slightly different numbers. What if we took this to be the prior distribution? Instead of somebody with a sibling who has CF, whose parents don't have CF, and that patient doesn't have CF, that was the situation we were in here, where the prior probability of them being a carrier is 2/3. What if this is just a random person chosen from the population? The prevalence of CF carrier status in the general population, it's actually one of the highest prevalences of these types of genetic diseases, is about 1 in 22, just a bit under 5%. So just a bit under 5% of just random people with no known family history. Just about 5% of them have, they're a carrier. They have kind of one bad copy. And then, of course, probability of them not being a carrier is 21 out of 22. If we took these as the priors and the test came back negative, then what would be the posterior probability or updated probabilities in light of the negative test result be? We'd expect their chance of being a carrier to go down pretty significantly, right? From 1 in 22 or about 5%, probably go down quite a bit, probably be pretty close to 0. And if they were tested for this and it came back negative and we had no family history or anything, we'd be pretty certain they're not a carrier at that point. Up here, it's still kind of, a bit of a toss-up. Still a 20% chance they're a carrier because of the combination of their family history and the test. But even with this person, under this sensitivity and specificity set up here, with 100% specificity, remember that means that if the test finds something, if the test comes back positive, or if the person's not a carrier, the test will never come back positive. So if the test comes back positive, it must have found something real, basically. Well, then, no matter how unlikely it is for them to start, well, no matter how unlikely it is for them to be a carrier to start off, if the test comes back positive under our scenario, there's actually 100% chance that they're a carrier and a 0% chance they're not a carrier. See if you can make that work out with the math. And then if you want to go even a step further, so these are the answers to these two, what if it came back negative, what if it came back positive? If you want to go a step further, redo this question, but maybe change the specificity to like 99% or 98% or something. And see if that makes a relatively small change here. Is it like, still like 98 versus 2? Or does it make a pretty drastic change? Just changing that specificity a little bit away from 100%. How does that change this answer? So that's an exercise to do to get a little more practice with this. All right, any questions so far? All right, let's look at a at a second example. So this is an example regarding mammograms, a type of screen for breast cancer. And these are actual numbers that I grabbed. These are reasonably accurate numbers. These came from a paper or presentation. Um, so these are like kind of reasonably accurate numbers for some types of tests for CF. Um, these numbers came from a journal article looking into the efficacy of mammograms for detecting breast cancer. So a mammogram type of screen for breast cancer has a false positive rate of 86.6 out of 1,000 and a false negative rate of 1.1 out of 1,000. So that means that sometimes the test comes back positive and the test says, hey, we see something that's suspicious for breast cancer. You should follow up with the doctor, maybe, do a little more testing, figure out what this is. But a false positive means the test indicated positive, but the patient actually doesn't have breast cancer. And we're saying that that happens, that the probability of a false positive is 86.6 out of 1,000. And then again, a false negative, test indicates negative, even though the patient does have breast cancer, 1.1 out of 1,000. The prevalence of breast cancer in this population, so the prior probability of a randomly chosen woman having breast cancer, randomly chosen woman at the age where people tend to go for mammograms, the probability that she has breast cancer before we know anything about the test is 1 in 38. And let's find what's called the positive predictive value of the test. That is, find the probability that the updated probability that a woman has breast cancer, given that she got a mammogram and the test came back positive, the mammogram came back positive. Okay, let's try to work through this. So I see my false positive rate. Well, I know that my false positive and false negative rates are related to the sensitivities and specificities, right? So my false positive rate, that is the test is positive, but the patient actually does not have breast cancer. So this is given the patient does not have breast cancer, what's the probability the test is positive? What's the probability the mammogram indicates breast cancer? That's what we have up here. That's 86.6 out of 1,000. That is this conditional probability. As a side note, we're not getting into like things that are like precancerous or anything like that. We're just pretending that there's like a stark dividing line, like cancer versus no cancer. And same thing with the mammogram. We're, not getting into, well, what if it's, too close to call or they're not sure. We're just saying, okay, positive or negative. So we're making things very black and white here. And then our false negative rate, that's also given to us. That's given the patient actually has breast cancer, what's the probability the test is negative? What's the probability the mammogram indicates that they do not have breast cancer? That's 1.1 out of 1,000. So of the patients who don't have breast cancer, some can come back positive, 86.6 out of 1,000, and some will come back negative. That's 1 minus 86.6 out of 1,000, or 913.4 out of 1,000. That's the true negative rate. Patients actually negative, test results negative. That's what we call our specificity. And then if we look at our false negative rate, probability of negative given breast cancer, of the folks who have breast cancer, they can either have a test result that's negative, 1.1 out of 1,000 chance of that, or they could have a test result that's positive, 998.9 out of 1,000 chance of that, just 1 minus this number. And that's our sensitivity. That is our true positive rate. Test indicates positive, patient is actually positive for the disease. That's our sensitivity. So what is the probability that a patient has breast cancer given that the test result was positive? That's probably what we're most interested in, right? But the information that I have is phrased the opposite way. I have things like probability of positive given breast cancer, not probability of breast cancer given positive. So I need to use Bayes' rule to flip this around. So that's probability of positive given breast cancer times probability of breast cancer over the probability of getting a positive test result overall. And again, just like last time, there are two ways to get a positive test result. We could get a positive test result and have breast cancer and actually be positive, or we could get a positive test result and not have breast cancer. So positive could be a true positive, positive and breast cancer. Which we could break up as positive, probability of positive given breast cancer times probability of breast cancer. That's the of the true positives. Or we could have some false positives. Probability of positive given no breast cancer times probability of no breast cancer. And just like before, we realize that my numerator is one of the terms of the denominator. So really what I'm asking is, of all of the positives, what proportion of them also have breast cancer? That's really what I'm asking here, right? And that's also pretty clearly what I'm asking here. Of all the positives, what proportion of them have breast cancer? Okay, so I have my prior probability of breast cancer was 1 in 38. That's before I knew anything about the test result. That's just the overall. If I randomly picked a woman of the age where they get mammograms, if I randomly picked one of them, what's the probability she'd have breast cancer if we kind of magically could just know? That would be 1 in 38. And then we also have probability of no breast cancer over here, the prior probability, that's 37 out of 38. I need to put in the probability of positive given breast cancer. That is the sensitivity, the true positive rate. That's this number, 998.9 out of 1,000. And then lastly, I need probability of positive given no breast cancer. That is this number, my false positive rate, 86.6 out of 1,000. All right, so now we need the calculator. So let me bring up the full screen. One thing that I do notice is I could multiply top and bottom by 38,000, clear all these fractions. And kind of similar to the car example, I see I have two countervailing forces. My test is pretty accurate, but it's also pretty unlikely that that a woman has breast cancer, right? So my test is fairly accurate, but not perfect. But I see this number is quite low relative to that number. But this number is quite low relative to that number. So the overall prevalence of breast cancer is low, but even though my test is pretty accurate, this number, roughly speaking, this number is a lot bigger than this number, in other words. So I'm looking for this ratio, 998.9 over parentheses 998.9 plus 86.6 times 37. And that gives me about 24%, about 23.8%. Now recall, probability of breast cancer before we had any information about the test was 1 in 38, or let's call that about 2.5%. So the positive test result increases our risk of breast cancer by something like a factor of 10, 2.5% up to something like 25%, 1 in 4. But a positive mammogram, I mean, it's still like 20, 25%, 1 in 4, 1 in 5 of, all women who were tested who get a mammogram and it's positive, only something like 1 in 4, 1 in 5 of them actually has a problem. A mammogram is a screen. A screen is a test that's essentially just given to everybody, roughly speaking, a certain population, not as a result of like we see certain signs or symptoms and therefore we send you to the test. We just say you're a member of the population, you get this, or maybe you're a member of a slightly higher risk population, like women over a certain age or something like that. So you get this, but we don't look at the person individually. We just say everybody who fits this, very generic criterion gets this test. So you might ask yourself, well, I mean, having that many false positives seems like a lot. I mean, this is for every one woman that we catch, there's something like 3 or 4 who are being put through a lot of stress, a lot of extra testing, maybe medical expense, maybe having to take more days off work, maybe having to go in for things like a biopsy or something that can be invasive or uncomfortable. That seems like a very costly. Uh, it seems like a lot of cost for the women who aren't actually positive, right? It seems like a lot of stress and expense and discomfort just to be told, oh, wait, you actually don't have anything wrong. You're all good. So why do we go through that? Well, the answer is that, kind of roughly speaking, there's a trade-off here between false positive and false negatives, or between sensitivity and specificity. We would love to just be able to make sensitivity and specificity both 100% or both super close to 100% and just have a great test overall. But the reality is that you really can't do that. You have to set a bar, right? And I like to kind of think of it this way. I think the easiest mental model is something like this. That if you think of glucose for, say, non-diabetics versus diabetics, and let's suppose that we were making a stupidly simple diabetes screen. We're just looking at glucose, one read of fasting glucose for the person, and then we're going to make the call. In reality, it's a much more complicated process than this because they don't want to make all of these errors, right? But what we have to do is we have to set a bar. Sometimes the diabetic person is going to happen to have a really low glucose number that day, really good glucose number. And sometimes the non-diabetic person ate a little too much ice cream over the weekend and their number might be a bit high that day. If I set the bar low and I say, if you're to the right of the bar, we're calling you diabetic. To the left, we're calling you non-diabetic. I catch almost all the diabetic folks. If you have diabetes, my test is very likely to call you diabetic. But unfortunately, we catch a lot of non-diabetic folks too. We're casting a wide net, so to speak. There's a lot of non-diabetic folks who I tell are diabetic, and whenever have them concerned or worried, or maybe they want to go on medication or something like that, or whatever it may be. So maybe I go the other direction. Maybe I set my bar very high. I'm much more narrow in scope for who I call a diabetic. Well, now there are very few non-diabetics who actually get called diabetic because my cutoff is so high, but I'm actually missing a lot of diabetics. There are a lot of folks who their disease is going to continue progressing, maybe continue harming their kidneys or their eyes. And, it's not going to be until a year or 2 years down the road, whenever their numbers get really out of control, that they make it past that. That's a cost on the other side, right? So there's a cost in each direction, right? When the radiologist looks at the mammogram reading and calls it basically thumbs up or thumbs down. Again, there's more nuance to the whole thing than what we're showing here, but just imagine they call it thumbs up or thumbs down. If that radiologist says, I see a little speck on there, I'm not really sure, what's their bias in a sense going to be? They're going to be more biased towards saying that's a positive mammogram because they don't want to undercall something. They don't want to say negative, have the woman leave the office, think she's good, come back a year, maybe 2 or 3 years later. People don't always follow up with doctor's appointments super great and all that. So she might come back 2 or 3 years later and her disease has progressed significantly over that time. That's a very bad result. But if we overcall it and she goes in and has, it costs a little more time or a little extra testing or something and finds out she's okay, kind of on balance, at least on a one-to-one comparison, that's probably less bad than how bad it would be to undercall a positive and let the disease progress for a few years unnoticed. So that's kind of where this line comes into play. Right? If we see something that's kind of marginal that the radiologist has to make a judgment call, I don't know, it could be positive, could be negative. They're probably going to be more likely to call it positive and make the mistake of overcalling rather than undercalling because they don't want the disease to progress for 2 or 3 more years if it is actually a disease. Um, and you might say, well, can't we just have better radiologists or better equipment or whatever? Well, sure. I mean, scientific advancements definitely drive these two numbers both towards 100%. If we have better imaging techniques or maybe AI assistance for radiologists or something like that, we might be able to do better on both categories. We could also spend more money. We could have, say, 2 radiologists view each image. And then if they both agree, that's the result. And if they disagree, we have a third one kind of break the tie. I think there are some systems that do that. But now you're, say, something like doubling the cost of a mammogram. We want to give these to everybody in the population, make them as affordable as possible, right? That can be a challenge there as well. So again, the question of like, where should we put this kind of philosophical cutoff between the radiologist calling it positive versus negative, or like where should we put the slightly more objective like line in a simplified scenario like this? To the right or left of this line is going to be diabetic versus non-diabetic. Again, that's kind of a wisdom question, right? That's a question of what are the costs and benefits on each side? How significant are they? Things like that. But we can at least inform and say that if you set the bar like this, you have a positive predictive value of 20 to 25%. This also means that, if you get a screen for something and it comes back positive, indicating disease, you should be concerned and definitely follow up with your doctor, but a lot of times maybe not be worried, not think like I certainly have the disease, right? It's often far from a certainty. And I think that's even more important these days when there's almost like this social media scrolling, like addiction to medical information, not quite addiction, but right. It's like, oh, my test result came in. They sent me a text. They sent me an email. They're like, you have a new test result. And I can go in and see what it is. And I can see it before my doc even sees it. And before they get a chance to look at it and interpret it in the context of their experience and my, all of my other health and all of that. So before they even get a chance to send me a message or whatever and say, hey, this is a little bit elevated, but not a big deal, or hey, this is a little concerning, maybe we'll follow up. Or if I'm looking at that and trying to interpret it, I might not do such a great job. So that's the answer of Why so many false positives? Well, because probably false positives are less costly than false negatives, right? A bit of follow-up, a bit of extra medical expense and time, maybe a bit of stress for a week or two until you can get in, and maybe a biopsy or something is, I think generally going to be considered less costly than missing a true positive and having the disease progress for a period of time. Okay. Any questions on any of this so far? Yeah, so screens tend to want false negative rates to be very low. They tend to want to be um, very high sensitivity. So if something questionable is there, it'll catch it. And what they give up is a lower specificity, that they cast a wide net and sometimes catch things uh, that they ideally would not want to catch. Okay, now let's look at example 3. We're going to shift gears quite a bit here. We're going to look at a machine learning example. Oh, give me a second here. My whole problem did not copy over correctly from the previous slide. Give me a second to copy the other data. That would be super helpful if we had the conditional probabilities. Sorry, I didn't notice that this didn't fully come over when I copied the slide. Okay, there we go. So this is an important component of the problem. All right, so what we have here is two charts. And this example, the context is that this is some information about different types of drivers. So let me actually put this one first. That'll make a little more sense. I don't know why that one didn't come over. All right. Okay, so we're presuming that in our the word insurance company and in our model, we have three types of drivers: good, moderate, or bad. So these are our three types of drivers. Good drivers get in fewer crashes. That means we have to pay less, fewer claims for them. We have to pay less money out to them. And that also means that we have to ask them to contribute less money to the pool. The way that insurance works is everybody who's under this umbrella of kind of similar insurance, they all pay money into the pool, into a big gigantic pot of money. That's what your premium does when you pay every month your car insurance. That money goes into a big, basically shared bank account in a sense between all of the drivers that are insured under that company. And then if you get into a car accident or something, you need to make a claim, you're asking to make a withdrawal from that account that contains your premium, but also everybody else's premiums too. So because the good drivers aren't really asking to take much money out of the account, they don't have to put a lot of money in. If we know that somebody's a good driver, we know that, okay, in the next year or two, you're not going to ask for much in the form of withdrawal, in the form of a claim. So we're not going to require you to put all that much in as a premium as your monthly cost to be insured. Moderate drivers get in more crashes, maybe more severe crashes. They're going to, on average, ask for a bit more out of that pool in the form of claims. So we ask them to contribute more into the pool to offset that. And if we knew that somebody was a bad driver, again, they're going to ask for a lot of withdrawals. They're going to ask for a lot of claim money on average. We ask them to contribute a lot then to offset how much they would ask for. So if I knew for certain, if I looked at this person and I knew they're a moderate driver, their premium will be 125 a month. Uh, I forget if I made this a month or a year or whatever. I actually don't even know what insurance prices are these days. But they've been going up and up and up. So maybe this is a month. Um, but if I knew that somebody was a moderate driver, I would set their premium 125 and uh, and I'd be done with it. But the thing is, I don't really know, just looking at a person, what kind of driver they are. I'm not omniscient. And frankly, that person probably doesn't know what kind of driver they are either. But I do know that if I look across the whole population, based on my experience as an insurance company over, say, the last 10 years, maybe in this area, I know that about 30% of drivers behave as good drivers. They get in crashes and make claims like good drivers, so I'll call them good drivers. About 50% of them are moderate drivers, and about 20% are bad drivers. So I have an interesting dilemma now. What if somebody walks in and I don't know anything about this specific person? They come in and they say, okay, I want you to write me a policy. What premium should I charge them? Now I might think to myself, okay, well, I could be an optimist and charge them the good driver premium, $75. But the problem is then that, well, they're only paying 75 in, and it's quite likely they're going to be taking more than 75 out of the pool, kind of on average, right? Because this person could very well be a moderate or bad driver who's going to make a lot of withdrawals, and that 75 that they're putting in is not going to counteract that. If I go like basically giving away insurance for cheap like this, then my pool goes to zero. And now the other people who are contributing premiums in, there's nothing left in the bank account for them to take out. So when your insurance company decides what premium to charge you, they're not kind of, it's not exactly the same as like deciding what to charge you for a good that Walmart sells or something like that. It's not just a question of what can the market bear. It's also a question of, well, I'm making a promise to pay you from this account in the future. And if we like give away too much insurance for cheap, that account gets drawn down and then there's nothing to pay anybody. On the other hand, I might say, okay, well, maybe I just want to cover myself. I'll just charge every new driver the bad driver premium, $250, until I get some experience with them. Then I'm safe. Then I'm not giving away insurance too cheaply. They're going to be paying in at least as much as they're taking out on average. But the other problem is that I'm in a competitive market. If I can really do better than this and I can support that mathematically, then I probably should try to do better than this, right? If I just charged all my new drivers the bad driver premium, my bank account, the pool, would just keep getting bigger and bigger and bigger because some of those people I'm charging $250 a month to will actually take on average $250 a month out of the pool. But a lot of them, 80% of them, are going to take significantly less than that. And my pool is just going to build up and build up and build up. And I could have gotten away with charging them less. And in fact, my competitor will realize that. And my competitor will undercut me. They'll charge them less than 250 because they realize that they don't need to charge them that much to sustain the pool. So then what should I charge them? Maybe we say, okay, split the difference and charge them the moderate driver rate. Charge them 125. And I think that's on the right, that's kind of going in the right direction. It's a little bit like using the mode or the median or something like that as a measure of center. And it's the right idea that we want to use some kind of measure of center. But actually, maybe we would want to use something like the expected value of the kind of premiums across the board, or a weighted average. What's kind of the argument here? Well, if I imagine that I have, let's say, 100 new drivers, and I have 30 good drivers, so there's 30 good drivers. there are 50 moderate drivers in here. And there are 20 bad drivers. If I had perfect knowledge, I would just look at the person and say, okay, you're a good driver, I'll charge you 75. You're a bad driver, I'll charge you 250, but I can't do that. So what I choose to do instead is I choose to take, each driver, and I choose to basically treat that driver as if they are like 30% good, 50% moderate, and 10% bad. So this is a very Bayesian perspective on things like probability. The frequentist would say, if I look at a driver, they're either good, moderate, or bad, period, end of story. The Bayesian can say kind of like, it's almost like this person's like in a Schrodinger's cat situation where they're kind of like some amount of good, moderate, and bad all at the same time. I just don't really know. So because I don't know which people to put into which bins here of my new drivers, my say 100 new drivers, I apportion them the other way. Instead of saying put all of this person in the good bin and all of this person in the moderate bin, I say like almost slice my people up, and put like all of their torsos in the moderate bin or something. In other words, I just want to take a weighted average. I want to look for an expected value. I want to figure out what's the expected premium that I should charge. So the premium I should charge them is 30% times 75 plus 50% times 125 plus 20% times 250. Let's come over to our calculator, type that in. So 0.3 times 75 plus 0.5 times 125 plus 0.2 times 250. And that gives me $135. And basically what we're saying is that across 100 people, what's 100 times 135? That's $13,500 that these 100 folks will be contributing to the pool. If I did it this way, where I split up, where I was omniscient, if I knew everything and I said, okay, I look at you, you're a good driver, I'll put you in the green bin, you're a bad driver, I'll put you in the red bin, and so on, I would have 30 people paying $75. I'd have 50 people paying 125, and I'd have 20 people paying 250. What's 30 times 75 plus 50 times 125 plus 20 times 250? It is exactly 13,500 being contributed into the pool, right? So I've made sure that my cash flow is the same, but I just accept the fact that I don't know whether a given person is good, moderate, or bad. So I have the same $13,500 from these 100 people going into the pool. They're going to ask for 13,500 out of the pool. Everything is balanced, but I just balanced it in a different way. Instead of saying, I'm going to put this whole person into the green or blue or red bin, I'm saying I'm going to treat this person as though they are a portion green, a portion blue, and a portion red. Or I have some amount of confidence or belief that this person is a good, moderate, or bad driver. Right? I have a high degree of belief they're moderate and a moderate to low degree of belief that they're good or bad. But here's where so that's one piece of Bayesian thinking, but here's where the Bayes theorem really comes in, is, okay, I have this new insured, I say, okay, 135 a year for the first year, or 135 a month for the first year. That's their premium. We go a year. At the end of that year, I look back and I notice that they got in one accident. I also might notice, or I also might know what good, moderate, and bad driver behavior looks like per year. So this chart is number of accidents per year. Oops. Fix that. All right. This chart is accidents per year for the types of drivers. In other words, good drivers, 65% of the time they get in 0 accidents in a given year, 35% of the time they get in 1 accident in a given year, and they never get in 2 or more accidents. Moderate drivers, 45% chance that they get in 0 accidents in a given year, 45% 1 accident, 10% 2 or more accidents in a given year. And for bad drivers, 30, 40, to 30% chance they get in 0, 1, or 2 or more accidents in a given year. So this, this say 10% here is saying probability of 2 or more accidents given they're a moderate driver is 10%. So I know something about the annual behavior, number of accidents for the different kinds of drivers. I started out with no information about the driver, so I just used this prior distribution for them. But now I've got a little bit of information. I've got some experience with them. They got in 1 accident their first year. Now I don't want to just say, okay, 1 accident, what's the most likely type of driver to get in 1 accident? Moderate. We're just going to call them moderate driver now. We don't want to jump ship from the previous experience that we had with them or knowledge about our population or whatever it may be. But we also don't want to just ignore this new information. We want to adjust their premium in light of our updated guess of what type of driver they are. So in other words, I knew that my priors, probability of good was it 30%? Yeah, 30%. Probably optimistic if you've driven on the roads recently. Probability of moderate, 50%, and probability of bad, 20%. This was my prior distribution. And now my question is, what's my updated probability of them being a good driver given that they got in 1 accident this first year? Well, I noticed that this chart up here gives me information conditioned on the type of driver they are. Probability of 2 or more accidents in a year given that they're a moderate driver. And what I want is the probability of them being a type of driver given accident information. I need to flip this condition around with Bayes' theorem. Probably they get in 1 accident given they're a good driver times probability of being a good driver over the overall probability that some insured gets in 1 accident in a given year. And my numerator, I have the same thing. My denominator, how can I get in 1 accident? I could be a good driver and get in 1 accident, or mutually exclusive. I could be a moderate driver and get in 1 accident, or mutually exclusive. I could be a bad driver and get in 1 accident. This is the event good and 1, being a good driver and getting in 1 accident. The probability of that split up. This is moderate and 1. And then we have our bad drivers. They could also get in 1 accident. So this is bad and 1 accident. Okay, now I think, ready to plug everything in. So my numerator, maybe I'll color code these so it's a little easier to follow. So my prior probabilities will be in blue. I'm going to not worry about the percent. I'm going to think of the percent just like a unit that's going to divide out. So probability of good is going to be 30. And then I have that same term in the numerator as the first one in the denominator. In the second term in the denominator, I have probability of moderate, 50 or 50%. And in the last term of the denominator, I have probability of bad 20 for 20%. And then I have my conditional probabilities. Given that somebody is a good driver, what's the probability they get in one accident a year? 35%. Again, I'm going to think of this percent as a unit. Each of these green factors will also have a unit of percent. So I'll just get rid of that, just divide that out. For moderate, 45. Oh, this one is 35 as well. 45 here for probability of getting in one accident in a given year, given they're a moderate driver. And then bad, 40%. And let's calculate this. Come over to my calculator. In my numerator, I have 35 times 30 divided by parentheses. Make sure to put the bottom in parentheses. 35 times 30 plus 45 times 50 plus 40 times 20. End parentheses. Let's check everything. Looks good. And this gives me 0.256 or so. So let's just say 25.6%. So what are my posterior probabilities? What's the updated probability of them being a good driver, given they got into one accident this first year? It's about 25.6%, right? This number went down a little bit from where it started out. They got in one accident, which is a little more characteristic of a moderate or bad driver than a good driver. So it's a little less likely that we think that they're a good driver still. But it's not like we just completely jumped ship, right? 30% of drivers are good drivers. This person could very well have just been a good driver who had kind of a bad year, and maybe in the next couple of years they'll do great. Now, what if I want to switch to probability of moderate driver given one accident? Well, that would be probability of one given moderate times probability of moderate over probability of one. Well, probability of one stays the same. The denominator is going to stay the same. These g's just change to m's. Or actually, instead of plucking out the first term in the denominator to put in the numerator, this is just exactly the middle term in the denominator. So instead of 35 times 30, I have 45 times 50, probability of one given moderate times probability of moderate. And instead of 25.6%, which was good given one, moderate given one, I'm actually going to use much the same calculation. I'll hit second enter, bring up the previous entry. The denominator all stays the same. I don't have to type that in again. That's nice. I just have to change the numerator to 45 times 50. And that's about 0.549. So about 54.9%. Right? Or probability of them being a moderate driver has increased a little bit in light of this 1 year of getting in one accident. And then since we know that this person is either good, moderate, or bad driver, we can just subtract from 100%. So I can do 100 minus 25.6 minus 54.9 to find the third. Or I could, of course, go and just use the third term of the denominator, pop that in the numerator, and get the same answer, 19.5 or so. So probably being a bad driver is about flat, but we took some weight off of being a good driver and put it onto moderate driver. It's a little more likely they're a moderate driver in light of this one accident, a little less likely they're a good driver, and about the same that they're a bad driver. And we're going to continue this, right? We're going to look at not only how did the distribution change, but then what does this effect have on their premium, say for year two? we want to update their premium as well in light of this new information. And you might imagine that this is how insurance companies kind of track your behavior over time and adjust your premium up or down, depending on how many claims you make, how many accidents you get into, what they perceive your risk to be in a given year. All right, let me stop the recording.